Okay, for motion control system here, we said it's one of the bar that or one of the criteria that we consider for classify the CNC machines. So before we go to know the type of machine, I mean the type of motion control system here, we need to highlight this statement. Part program is made for tool motion. That means we said the NC machine consists from three main parts. The first part was the instruction command or part program. We call it the part program. And the second is the MCU. The third is the machining tools. So when we talk about the part program here, or the first component of the NC machine, actually this is made for the tool motion. That means we are going to write the program to control the motion of the tool in the in the CNC machines. So we need to define the path of movement, because we for example, if you have this surface here, the surface of our product or our or the work piece that we want to manufacture or want to make some modification for it. For example, if I want to make a hole in this part, then I want to make a hole and another part here. I need to make a hole in the third part. If there is operator or human who make this one, so the thing he will do it manually. For example, he will measure what is the distance or what is the length from this side until this place and the length here. To know where to place this first hole. Then he will go there. Also, he makes some measurement from this side, some measurement from this side, some measurement from this side to know where is the place for the second hole. Then he do some measurement here to know what is the place for the third hole, for example. So this is, it was operator. If there is operator for the manual machines. But if we are using CNC machines, so no need to do all these things. What we need to do, only we need to write the part program with the specific coordinate to define where is the first hole, how the machine will move. Is it right, left, up, down, front, back? Then the workpiece will be moved to the spindle to make the second hole. Then where will be the third hole and how the machine will move from the second hole to the third hole. So we need to define this path of movement with the coordinates for every hole by using this part program. So the part program here is more responsible to define the motion of the tool with the coordinates of the task we need to perform. I want to perform this task. What is the distance from this part, from the x-axis? What is the distance from the z-axis, and how I move on the y-axis, and so on. So this is what we mean by the part program. So it's more related to the motion or to control the motion of the machines. So some of NC process here or NC machines are performed at discrete location. Discrete location means, for example, this is a discrete location. I want to make drilling at this point, and they have another task will be on this place. So it is discrete, it's not continuous. Discrete means, when we say discrete signal, we have, for example, for continuous signal, for example, we have at every time we have a value. But for the discrete, only we have some task at specific place. So we have like this we call it discrete. So some of NC process here perform discrete location on the work part. So for example, we want to perform drilling or spot welding. You please correct this word in the slides. It was welding. It is spot welding, not welding. Okay. Other NC process here are performed while the work head is moving. So when we say discrete, that means I want to make a hole in this place, then I want to move to the other place, then I move the hole. Between these two holes, there is no task need to be performed. From this point to that point, the machine is not required to perform any task. So we call it discrete. But in the continuous one here, the machine will, for example, if I want to cut this blade or this sheet of metal sheet, I want to cut, so the cutter will move continuously on this line, for example, from the beginning to the end. So it is a continuous task. It's not just discrete. So the cutter will move from this place continuously until the end, from the start point to the end point. So this some of the process which is the machine required to perform action during the movement, like turning machine or milling machine and so on. So there is type of movement here, like straight line. Some of machine need to move straight line. If I want to make like straight cut here or straight line, so the machine will move directly. Or sometimes the machine will move in a circular form or in the curved form. Okay. So these are the three types. There are three types actually for motion control here. Actually, the original there are two, but the third one is just combination of both. So the first type we call it point-to-point motion control system. Point-to-point, that means we have the first point here. This is point 1, for example, and this is point 2, and then point 3. So I need to define in the point-to-point here. We need to define the first point and the second point of motion. It's not required to do any task between these 2 points. So we are going to make a hole in this point, then the machine will move to the second point and make a hole, then move to the third point and make a hole, and so on. So this will be the machine is required to move from a location to perform an operation at that location. So for example here, the drilling machines, the bushing machines, and feed motion and cut-off machines, and so on. So all this one, this is the spindle here, and this is the workpiece that we want to modify or want to do some task on it. So this machine will move from this point. I mean, it will take action at this point, then it will move to the second point. It take another action, then it will move to the third point. It take another action, then it will return to this point. So this we call it point-to-point control motion system. The second type we call it straight cut systems. Straight cut system here is more related to the axis here. So if I have 2 axes or 3 axes, the machine or the spindle of the machine here or the head of the machine will move first in one direction until finished, then it will move in the other directions. I mean, it's not like the previous one. The previous one is defined by points. I will give the coordinate for the point 1. For example, it is 2, 1, and 5, for example. This one is 3 and 6. I mean, this will be defined by coordinates for points. But in the second one, the coordinates here only defined on one axis. So we are going to move on x-axis from point 1 to point 2, point 3, and so on the x-axis until finish, until reach to the end of this product on the x-axis. Then the machine will move to the other direction on the y-axis. It will perform the task. So this we call it straight cut system. Example also the same, feed control here for drilling machine and also workpiece handling. So this is the workpiece. It has 3 directions, 3 axes. So in the x-axis, it will perform the task. Then it will move to the y-axis. Then it will move to the z-axis. Z-axis is more related to the thickness or the height of this product. The third system, which is continuous path system. So the continuous path system already mentioned, we said the machine here is required to perform a continuous movement. Move, and also during movement, it needs to perform a task. It's not just move from one point to another point. No, between these 2 points also, it needs to perform a task. Between the other 2 points, it needs to perform a task. While moving here, it needs to perform some task, either make a hole, for example, make milling, make turning, and so on. It depends on what is the program task. So for example, for this machine is milling machines and lathe machine and so on. So you can see here, this is the work part or the workpiece that we place in the machines, and we want the machine to perform. You can see here, it's not easy to define one point only. I mean, I cannot just make this point, cut at this point, then go straight. No, it's not like the previous one, straight cut. No, I need to cut at this point until here. Then I change the direction to that way with a specific angle. Then I make a curve. After I make a curve, I make another curve here. Then I make straight back. Then I make this line with angle. Okay, so this we call it the continuous system. So the continuous system here, the machine need to perform a task in a different direction or in the different axis, depends on the defined path from the start point. This is the start point, for example, and here is the end point. So it will go there from start point, up, curve, up, left, and down. So this we call it the contouring system or continuous system. Okay, so we call it continuous system. Also, they call it also contouring systems. So it can be 2-dimension, 2D continuous path control. That means in 2-dimension only, like X and Y, and also it can be for 3D, X, Y, and Z. I mean, it can be also related to up, down, left, right, front, back. So for the 3 directions. Is it clear the motion control system here? The type of motion control system. You still there?
Yes, sir.
Yeah.
Yes, sir.
Okay. Okay, so the motion control, I will ask, after that I will ask you, okay? Because we want to continue our questions. So the motion control here, how we perform this motion control? We said this machine or this head of the machine or this spindle of the machine will move. I mean, will move left, right, up, down, back, front, and so on. So how this spindle or how this tool or how this machine will be controlled? The control of this machine uses the servo controlled motors. This is one, I mean the servo motor here. The servo motor is one of the motors which is used to control the motion in the CNC machines. It's not the only one. There are other type of controller or there are other type of motors which can be used, like stepper motor and other electric motor like DC and AC motors and so on. But the servo motor is more, or it has more functionality because it can move in the axial. It's not only rotating; it can rotate and also it can move on the axial movement. So this is the motor. For example, it will rotate this lead screw. This lead screw, the movement of this lead screw, even it's rotating, but also it will move this table along this lead screw. So this is the table here of the machines, and the lead screw here is fixed with the table or with attached to the table here. There is some part which or mechanical part which allow this table to be moved along this lead screw. So the AC servo motor here or DC servo motor, it depends on the type of the, I mean, either AC or DC servo motor, which used to control this movement of the lead skip. The leads, I mean the lead screw. The lead screw here will move the table. So the table can go left until the end, then go right until the end. So it allows the movement. So how we can control this motor here? I mean the movement of this motor, how we can control? It can be controlled by using a servo controller. So there is a drive or servo drive, usually we call it servo drive. Is a machine or a control, I mean is a controller or equipment which used to control the servo motor movement. So what I need to control in the servo motor, I need to control the speed of rotation for the servo motor, also the position of the servo motor lead screw. So not only the speed, also the location. For example, the speed is, for example, is 100 RPM, but where is the location at this point? Where is the location at that point? Where is the location at that point? Also need to be controlled. So usually we have a comparator here inside this servo controller. In addition to the counter, this counter is connected to the encoder. Usually this encoder is represent the sensor because it will read the pulses from the servo motor here, the generated pulses during due to the rotation of the servo motor, and these pulses will be converted into speed values. So encoder here represent like speed sensor, speed or velocity sensor. So it will convert the generated pulses from the rotation of this motor into a readings in RPM, for example, which is a revolution per minute. So then this RPM will be sent to the servo motor. Okay. So usually this is the main component for the servo motor control CNC. It's actually, this one is not the, if you remember last time when we said the CNC computer cannot control the machine alone. I mean, not the computer who control. Computer, it has the software inside, but what are the hardware or what are the interface which connect between the computer and the machining? This one part of this interface, which is the servo motor control, the servo motor controller. So the servo motor controller here, it has command sections. So this command section are going to give the input signal to the motor. So what is the speed that we need and what is the position that we want. Okay, so it will give the servo motor the command which define the speed and also define the location. Okay, so this we call it the target values or the reference values. So this target value or reference value will go to the servo drive, and this servo drive represent, as we said, it's equipment or amplifier or electronic circuits inside it, which will read these values and convert them into output. This output will go to the motor in order to perform the movement. I give, for example, I want the speed to be 100 RPM. I want the position. I need to define the position here, the coordinates for the position. I give it to the servo drive. The servo drive will send it to the servo motor. So the servo motor here will perform, will running at this specific speed and this specific, and move the ball screw here into the specific coordinates that defined by the input here. After that, the encoder here will read what is the actual value of the speed. I give, for example, 100 RPM, but the actual value, for example, it is 90 RPM here. It's not achieved or it's not reached to the set point. Then the encoder will read this value and give it as a feedback to the servo drive. The servo motor will send this signal to the controller. The controller will increase the pulse. How we can increase the speed or decrease the speed? We need to use some of speed controller. Speed controller, for example, sometimes we need to adjust the voltage, we need to adjust the current, and so on. So this value, which used for power electronic circuit or power electronic drives, it will adjust and then it will send. Since the speed is less, I want 100, the actual is 90, so I need to increase the voltage, for example. So it will send higher voltage to the servo drive. Servo drive will send higher signal to the motor. Now the speed of the motor become 100. This in the case of since we have a feedback here, so we are talking about closed loop. If there is no feedback signal, so this will be open loop. Later on, we are going to talk about this closed loop and open loop. But now I want you to know that how the signal is flow from the controller to the servo drive to the motor here or the servo motor, and this servo motor will move the table. This table actually is the table for the machine, for drilling machine, for milling machines, for lathe, and so on. So this is the table of movement. This table actually, it has this controller can also be used for controlling the movement of the head or spindle of the machines. Each part or each movement part of the CNC machine, it has own control mechanism. Okay, so how to control the table to be moved left, right, how to control the spindle to move up and down, how to control also the workpiece which I fixed on the table. Also, there is another mechanism used for that. So for the servo control here, after I got 100, for example, now the feedback signal will be, oh, okay, that the servo motor is speed at 100. So the target value here will not be changed. The signal will not be changed. No up, no down. Previously, we said we increase the voltage, but now the voltage will stay constant, the current will stay constant, and will keep this speed at 100 until I give another order, which is, for example, I want to decrease the speed, I want to increase the speed. It depends on, and the signal will flow from the servo drive into the servo motor, then back from servo motor to the controller. This is the block diagram to show how the servo motor is connected to the controller here. Same like the previous one is like more schematic diagram. It shows the more the devices. Here it's more on the line. I mean the block diagram for the signal. So here we have the controller. Here we have the command either up or down to the servo drive. Servo drive will send to the servo motor. Servo motor will control the lead screw here, left, right, depend on the enter position, and the speed here depends on the enter speeds. So the feedback here, we have two feedback. We have feedback for position. We have feedback for velocity or speed of the rotation. The feedback here will go to the controller. The controller will adjust the output signal here and send again to the servo motor, again to the servo, and so on. So it's like it's a closed loop with a feedback system to keep the servo motor at specific speed and at the required or the desired position on the x-axis. So this is how the servo drive looks like in practical, and this one is the servo motor in practical. So this is the definition of servo motor and servo drive. What is the definition? I mean, what's the difference? The servo motor is more on the mechanical or rotation part of the servo devices, and servo drive is just electronic amplifier, which used to control the output signal which sent to the servo motor. Okay, before we move to interpolation, is it okay? Tell her for the servo motor, I mean for the motion control system. I will ask. Mr. Ikmal.
Yes, sir.
Could you just state the type of motion control system?
Sorry, sir, again.
State the types of motion control systems.
Type of motion control system.
Type of motion control system, yes.
Open loop, sir.
One loop, are you sure?
Maybe, sir.
Maybe yes, maybe no. Okay. Last time you answer or not? No. This is the first time I ask you, yes?
No. You already asked me twice, I think.
Really?
Yeah.
Okay, good. You are lucky. So every time I ask you, you got either +2 or -2. The previous one?
Okay.
Okay, thank you. Okay, now, I want one from the yellow. Okay. Suhaila. From yellow zone. Suhaila.
Yes, sir.
Yes. Could you state 3 types of motion control system?
The point-to-point system,
Point-to-point system,
straight cut system, and continuous path system.
Okay, thank you. Okay. System then. Okay, Sean.
Yes, sir.
Which type of this motion system need to use interpolator?
Interpolator.
Yes, she mentioned 3 types of motion control.
Yes.
Which one is required interpolator?
And the continuous path system.
Okay, continuous path system. Okay. So interpolator is required for continuous path because why we need to use it?
Because it's like a closed loop. It needs to continue after a process.
Okay, the machine is required to perform a task during the motion. Okay.
Yes.
Okay. Thank you.
Thank you, sir.
Okay, let us continue. Okay. So now we are going to talk about the interpolator. We said the continuous system here or contouring system is required interpolator because we need to define a series of coordinates. We are not only talking about one position or one location to perform a task. The machine is required to perform a task along a continuous path. So during the movement of the machine, there will be a task to be performed. So we need to define a huge number of coordinates for the machine to go from the start point until the end point. For this task, we need to use interpolation or interpolator. So interpolator here is a component or a device in the attached to the MCU of the machine or the CNC machines to generate coordinates for the continuous movement of the machines, or I mean it's like to draw the path. So this interpolator here will define the path of the continuous path that we mentioned before. If we see here, we said we have a continuous path. So this is a continuous path. We have many coordinates here from the start point here at this point until we reach to the end point. So we need to define coordinates along this path. So who will generate these coordinates? It is the interpolator. So interpolator is a device that will generate these the coordinates for the simultaneous movement of the machine. The interpolator actually either can be electronic hardware, so it can be a device. That means a device is electronic hardware in the case of numerical control machine, or it is a software program in the case of the CNC systems. So interpolator here, it can be hard devices or hardware in the case of the NC machines, and it is a software in the case of the CNC machines. So in the CNC machine, we have a software which may or perform the task of interpolator device in the NC machines. So the interpolator here, these are the two tasks need to perform or two function of the interpolator here. It calculates the individual axis velocities to drive the tool along the program path of the given feed rate. So it needs to calculate the individual axis velocity. So for example, if the machine will move on the x-axis, what is the speed of this machine? What will be the speed of the machine on the x-axis? What will be the speed of the machine on the y-axis? What is the speed of the machine on the z-axis, and so on? Okay. The second is to generate thousands of intermediate coordinates along the program path. I have path from this point, then left, right, up, down, and return back again until reach to this point. So I need to generate all coordinates. What is this point? How many x? How many y? How many z? What is this point? How many x? How many y? How many z? And so on. It will generate thousands of points here along the path in order to allow or to guide the machine to move from the start point until the end point on the workpiece. So we have different methods for interpolation here. We have 4 methods actually for interpolations. The first is linear interpolation, and the linear interpolation here is just define a straight line between 2 points. So you have the first point, you have the second point, the interpolation will generate a line here. Straight line between 2 points. It's just or ask the machine to go from point A to point B straightly. The second is circular interpolation. The circular interpolation here, it's in the form of the circle of or semicircle of the path is curved, is not a straight line. So here need to define this is the first point, for example, this is the second point, third point, fourth point, and so on until we reach the 5th point. either we complete the circle or not complete the circle, but also this represents a part of the circle with some or with the measurement to of the diameter or radius and so on. So circular arcs defined by starting point, end point, center, or radius. In this case, we need to define either the diameter or the radius of this curve. So we call it circular. The third is helical interpolation. So the helical interpolation here is just is more on the circular plus linear motion. So it will move, for example, from point to point as a circle here or as a coordinate. Then also it need to move straight line. So it can be, for example, on x-axis, on y-axis, z-axis, and so on. It will combination for both circular in addition to linear motion for the for the machine or for the bat. The fourth, the last type is parabolic and cubic interpolation. So it's more complicated, like this figure here is more complicated, which consists of spherical or curves with lines, and this will be defined by using some high order equations. High order equation to define what is the semicircle here, what is the the spherical shape, and more 3D shapes. Okay, so this all type of or method of interpolation, as we said, it can be defined by using device in the NC machine or using the software and the equations using the CNC machines. After the interpolator draw these lines or this path for the machine, the movement or the motion of the machine will follow this path from the start point until the end point. Depends on the generated coordinates. So the machine will move from point 1 to point 2 to point 3, 4, 5, 6 until reach to the last point. So it depends on the defined coordinates by the program. What is important in the interpolation here is the tolerance. Tolerance is the the definition. The tolerance here is more related how accurate or how close is the path generated by the interpolator to the real path. So the interpolator here will generate a path which is close to the real path, but it's not exactly the same as the real path, because as we said here, we have some circular, we have some spherical surface, we have some 3D dimension and so on. So it's not that accurate. We have some tolerance. So as this value of tolerance is small, that means the interpolation method is more accurate. So when we have this small or we have this small tolerance, if we have a huge number of coordinates, if I define one point is here, the another point is here, that means the movement between these two points can be straight line, can be like this one, can be like go through and so on. So we have multiple. If we have only 2 points, we should have the machine may follow a different path. But if you have 1 point, another point is too close, so the path is more accurate. So the machine should follow this point because the machine will move from one coordinate to the another coordinate. So it will be more accurate. So the smaller the line segment, the better the accuracy. Smaller line segment, that means that if I have 2 points, as this line is small, I can ask the machine to move from this point to that point accurately. But if this is long or the segment is high, is longer, so that means the machine maybe go around this one. So it's not that accurate. Okay, so the tolerance here, it can be inside, outside, or inside, outside. So when we talk about the circular, the second type here, which is circular interpolation. Circular interpolation, you can see here, as you can see here, this is the point 1, point 2, point 3, point 4. You can see the dot lines which connect between point 1 and point 2. It's not exactly on the original path that I want to follow. but this is the path, the dash path, which is generated by the interpolator. So there is some difference between the actual value and the actual value, which is the continuous line, and the interpolator generated path, which is the dash line. So this difference between the two paths, we call it the tolerance. So you can see here in the circular interpolation here, we have three types of tolerance. We have inside tolerance. That means when we draw the line, I mean, the generated line, this is the actual curve, which is the continuous path. And here is the line that will be generated to approximate the circular, because actually when we draw line, I mean, when we follow coordinates of 2 points, we can only draw lines. We cannot draw a circle, correct? So when we draw a line here, this is line until this point, this line until that point, this line until that point. So the second line here, which is the red colored line, this is the straight line segment approximation for the real line. It's approximation for the actual line. And this, the dash here, the difference between this dash point and the actual point, it represents the inside tolerance. So the inside the tolerance here is caused by due to the difference between the actual value and between the actual curve and the curve that we draw by using the interpolator. Okay, so this is in the case of inside tolerance. For the outside tolerance here, also we draw the line to represent the actual curve from outside, not from inside. So the same here, there is a line, and the tolerance is represent what is the difference between these 2 points. You can see this is the tolerance here. This is the difference between the actual value and the line, or the line which is drawn through the interpolations. Actually, these tolerance value are very small, but here just to show that usually the path which is generated by interpolator is not exactly the same as the original path is required to perform the task. There is some difference, and this difference we call it that tolerance. It can be from inside, it can be from outside, also it can be from inside and outside when we try to approximate the real path by using lines, because our machine will not go like this way. Our machine will move left, right, front, back, up, down. So in order to move from one point to another point, we need to draw a straight line of approximation. Okay, till here okay? Any question about tolerance, interpolation methods? You still there or not? Any answers?
Sir,
Yes.
can you explain a bit on small tolerance?
Tolerance, we said in the circular interpolation here, we cannot define the path exactly as the circle here. Okay, so the interpolator will approximate the real path or the real circular path by using lines. This line can be line from inside, can be line from outside, depends how the setting for this interpolator. Okay, when we represent these lines, when I draw line and the original is a curve, there will be a difference between the original value and the line one, between the curve and the line. So the difference between these 2 points, if this point, for example, is at, if we say 2.1, and here this one is at 2.09, for example. So the difference here between this one will be like 0.01. So this we call it the tolerance, the difference between the actual curve and the curve that represented by interpolator using the lines. So you can see here there is a line, The outside curve is the actual curve here. The actual curve means the curve that we need the machine to move around or to follow in order to create, for example, or to perform a task on the product or on the workpiece. I want the machine to move in this circular or curve line path. What the interpolator do here in the case of circular interpolation, it will not draw a circle. It will represent this circle by using a series of line which is consists of line between 2 points. So it will draw line from inside, for example, or draw line from outside. In both cases, when draw line from inside or outside in order to represent the curve, for sure you have a different. It will not be exactly the same, because you can see here, this is the dash one is the generated path inside I mean the generated path when we connect the lines. The line here, this is the first line, the second, I mean the first line, the second line, the third line. If you compare the actual curve with the line, there is a difference. So this difference, we call it the tolerance. Tolerance is the difference between the actual value and the generated value by the circular interpolations. So this tolerance can be from inside when the interpolator represents this curve from line using inside. That means it will use coordinates which is less than this point. If we say this, if we represent this one using x-axis, for example, I mean, or y-axis or z-axis, if I have axis here, so you can see this point is higher than that point. This point, the coordinate is here, and this is x-axis coordinate, and this one. So you can see here, there is a difference between the actual curve and the curve generated by interpolate here. In the case of using inside, there is this will be less. In the case of using outside line like we have here, so this will be like, for example, like this one. So also it will have a difference. So either the tolerance to inside or tolerance to outside or tolerance to both, this represents how accurate is your interpolator to create the path for the machines. How we can control this one? Actually, usually for the tolerance here, by using smaller segments. That means when you use smaller segment, instead of draw line from this point, for example, to this point, this will be higher tolerance. But if you draw line, just small line to this point, then draw another line to this point, then another line to this point, for example. I mean, you just segment this line into multiple 2 points line, but with a small segment, that in this case, you are going to increase the accuracy. So the generated path by the interpolator will be too close to the original one. So no more tolerance. Okay?
Okay, sir.
So NC axis here, we already talked about system coordinates in the first chapter. I mean the coordinate system for NC machines in the first chapter, but you just highlight that part and how the axis or coordinates is important to the NC machines. Now we are going to see how we can represent the program of the CNC machine by using this NC axis. How we can define the coordinate to move the machine from one point to another point. Okay, so depending on the machine specification here, the coordinate axis can be designed or translated into a rotary axis. Previously, we mentioned that we have, for example, we have X, Y, Z, and also we have around X, there is one rotary axis, around Y, there is rotary axis, around Z, there is rotary axis. So we define also this rotary axis, we give them a names as we see in chapter 1. For example, we say A, B, C, we say X, Y, Z, we have also U, W, V. All these coordinates usually used in the CNC machines. So for axis to be controlled here numerically, each NC requires electronic path measuring system and also servo drive. As we see before, the electronic path here is used to measure where is the position, and this position will be given as a feedback to the servo drive as we see here. So this is the position here. When we talk about the position, we are talking about the coordinates of the point. So we need to measure this, or the servo drive will measure these coordinates by using a positioning sensor, and it will feed back to the controller of the servo device drive. Okay. So then we have here letters, as we mentioned before. We have letter and we have a number. Need to define the direction and the movement of the spindle here across the work piece or the work table. So this is the Cartesian coordinate, all we know. I am not going to spend any time for this one. So Cartesian coordinate, we need to define, as we already mentioned in chapter 1. We need to define the coordinates for X, the coordinates for Y, the coordinate for Z, if you have 3 axes and so on, as the points, okay? So we said there are another coordinates like polar coordinates, and also we have the attitude, latitude coordinates that use with GPS and so on. So all these type of coordinates, but for the CNC machine, it depends on the Cartesian coordinates, which is using the rectangular form. Rectangular form, that means we are going to define values for X, values for Y, and also sometimes value for X, value for Z, and so on. So this we call it the rectangular coordinates or Cartesian coordinates of the machine. So these coordinates are used to instruct the machine tool where to move on the workpiece. We said we have spindle here, and we have also the workpiece. We need to move this spindle. This spindle will be fixed, and the workpiece here locating on the table. The table is moved by using a servo motor. So the table will be moved left, right, for example, front, back, and this will be locate the spindle which go up or down. Okay. So we need to define this coordinate in order to design our path for the machine to perform its tasks. Okay, so we have here X-axis, Y-axis, and Z-axis. We already mentioned before. X-axis is used for horizontal movement, right or left. Y for the table here. Then Y-axis is the table cross movement, so either to the table or away from the column here. So depends on the place of the spindle. So the table here will go either go this way or away from this way. The axis X will be go left or right. Okay, and the Z-axis here can be vertical movement for the knee or spindle, either up or down. So usually for the CNC machine, we need to define the origin point. This I already also mentioned in chapter 1. I said this is the point of origin or 0, 0. Usually we need to define some reference point in order to move from this reference point. If I said move from the origin 2 to the right, that means I'm going to this 2. If I said move from the origin 2 to the left, so it will go to this -2. If I said go 1 to up, so it will go to 1 here. 1 down, it will go -1 and so on. So this was the 2-dimension plane consists from 4 quadrants: Q1, Q2, Q3, Q4. This you already know. Q1 is all value of X positive, value of Y positive, here positive, negative, 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 positive, and negative. So here, this is the coordinates and how we can relate. Usually we need to move as we see the path, go left, up, right, down, and so on. So if I want to draw the path for the machines, I need to use these coordinates in order to define how the machine will move. We have also for the 3-dimension here, coordinates planes. As you can see, the 3-dimension coordinates planes, you have X, we have Y, we have Z. It will be like this one in the 3D. So X will be left and right, Y will be away or to, Z will be up or down. So this is the 3-dimension coordinates for the plane. This is some standard that we need to follow during the using the defining the coordinates for the CNC machine or writing the program for CNC machines. Usually the longest horizontal axis movement is X axis. So X axis, it can move left, right, but the scope of movement or it can move for the longest distance, either left or right. For up down, it has limitations. Also for the front back, also it has limitation. For Y and Z axis, they have more limitation space to move. Okay, so the table will move left, right is more free to move left and right. It has more space to move. Okay. Secondary axis, usually we use UVW. This is when we define the program. We are going to use X, Y, Z for the original axis. We are going to use UVW for the parallel axis. That means if you have X axis, but X axis is shifted by some distance, we call it, for example, U axis. So this is X axis, the original one. And if this X axis is shifted for some distance here, so we call it Y axis. The Y axis, U axis, I mean. The Y axis, if moved, we can call it V axis or W axis. Then we have ABC, refer to the rotary motions. As we mentioned before, we said if X axis is moved, we have A axis rotation here. If B for Z, I mean for Z and C for Y, or this definition. Also I, J, K. This is only just symbols that we are going to use during writing the program for the coordinates. So this is some standard for people use it when writing the program for CNC machines. R represent here the radius of the circle, U and V words, incremental movement, X and Z, primary axis, and so on. So all these parameter or these abbreviations or symbols are used when writing the program for the CNC machines. So this is some guidance with, okay, I will just finish this slide, then next lecture we are going to continue with incremental and absolute coordinates. So here is the guidance to follow when using the system of rectangular coordinate. Rectangular coordinate, this one we said 2, 3. We call it rectangular coordinate. We are not using the angle like polar coordinate when we said 5 with the angle of 45, or when we define the angle of latitude and for the GPS system and so on. Okay, so the rectangular coordinates, just you need to define what is x-axis, what is y-axis, or what is x-axis, what is z-axis, and so on. So use reference point on the part itself. So reference point means you need to define what is your reference, either 0 and 0, or you want to use another references. If I use 0 and 0, so all the values will be measured to the 0 of 0. If I go right, I will measure how many units I go to the right, how many units I go to the left, and so on. Then use Cartesian coordinates specifying x, y, z planes to define the part surface. Okay. Then establish reference planes along part surface that are parallel to the machine axis. So you need, after you define the original or the reference part here, you need to establish the reference plane along the part surface. So on the part that you are going to work on it, you need also to define your coordinates here. Establish allowable tolerance at design stage. So you need to define the tolerance. What is the error that you accept for your work? I mean, what is the tolerance or the difference between the actual path and the interpolator path will be generated. Also describe parts so the cutter path may be easily determined the program. When you need to describe the part here, you need to define the part. Also dimension part, so it is easy to determine the shape without calculating the question. So these some steps you need to consider when you write the program for CNC machines.